Hello, welcome to the 7th lecture of our graduate combinatorics course, Math 688, which is offered online during the fall semester 2021 at the University of Delaware. Today, we are going to talk about derangements, and more precisely, we are going to be interested in determining the number of derangements on n elements. As we mentioned last time, a derangement is a permutation in Sn for some natural number n, such that sigma has no fixed point. So sigma of x does not equal x for any x between 1 and n. And our notation will have dn as the number of derangements in Sn. So before we get to work on this, on a general formula and other properties of this sequence, let's do some small examples. When n equals 1, we have only one permutation, the one that maps 1 to 1. That is not a derangement, so d1 will be 0. When n equals 2, we are going to have two permutations, the identity permutation and the transposition of 1, 2, which is a derangement, so we get d2 equals 1. When n equals 3, we are trying to count those permutations that have no fixed points. Therefore, these permutations are going to be either a cycle of the form 1, 2, 3 or 1, 3, 2. And that leads us to conclude that D3 is going to be 2. Okay, D4, we will come back to it later, but you can think about it a little bit. D4 can be counted, can be determined by noticing that the derangement on four elements is either a product of two disjoint transpositions, or it's a cycle of length 4. Well, we'll come back to D4, D5, and so on. For now, let's just state a proposition which will give us a recurrence relation relating the dn to smaller values of n. To smaller values of dn minus 1, dn minus 2. So let n be greater or equal to 3. Then dn equals n minus 1 times dn minus 1 plus dn minus 2. Okay, so this is a recurrence relation unlike any others that we've seen until now. Before we use it, we should first try to prove it. So how are we going to go about it? Well, we are trying to count, so those permutations, so let's say let sigma be a permutation in Sn, that is a derangement. And sigma, if we look at it in a two-line notation, will look something like this. Let's call this elements on the second row, sigma 1, sigma 2, sigma n minus 1, sigma n. Okay. Now, because sigma is a derangement, we know that in each column we don't see the same element twice. So 1 is different from sigma 2, 2 is different from sigma 2, n minus 1 is different from sigma n minus 1, and n is different from sigma n. And we will focus on, we'll pick one of these entries, let's say the last one, n, and we'll see what happens there. Okay, so let's have our permutation again. So let's call this entry in the position n, let's call this entry x. So x denotes sigma n, which is different from n. Okay. Now, we're going to have two possible situations. So we're going to have case 1. When we look at the entry corresponding to x here, because since x is not n, x has to be between 1 and n minus 1. Case 1 is going to be when sigma x equals n, And case 2, it's going to be what happens otherwise, which is sigma x does not equal it. Now, in terms of counting, what we're doing is we have here the set of derangements in Sn, and essentially we're splitting them into two parts. The ones on the left are the ones in case 1 where sigma x equals n, and the other ones are going to be the ones that have the property that sigma x does not equal n. And we are going to count those derangements for which sigma x equals n in case 1, and we're going to count the remaining ones in case 2. Okay. So that's our plan. So let's take each case aside and analyze it. In this, in the first case, sigma, we have 1, 2, we have an x, n minus 1 n. N is mapped to x, and x is mapped to n. Okay. Now, first of all, how many choices do we have for x? There are n minus 1 choices for x, as x can be anything between 1 and n minus 1, so it belongs to the set 1 to n minus 1. Okay. And now let us ignore for a second these two columns. So the x and n, they form a transposition, and from there we are going to ignore those columns for a second, and we're going to have some permutation. Let's call it sigma prime, which is on the top. We're going to have 1, 2, n minus 1. So there's no x and no n, and they map to sigma 1, sigma 2, sigma n minus 1. What I want to say here is that this permutation, sigma prime, my claim, sigma prime is a derangement on a set with n minus 2 elements, which is the set n from which we remove x and n. And this is pretty obvious because sigma was a derangement, and we didn't change anything. The only thing we did from sigma is to delete two columns. Therefore, we couldn't have created any fixed points. Therefore, sigma prime must be a derangement. So sigma prime is a derangement. So that's the argument. Now, how many possibilities do we have for sigma prime? Well, sigma prime is going to be a derangement. It's not exactly on the set 1, 2, all the way to n minus 2 necessarily, but it's a derangement on a set with n minus 2 elements, and the number of derangements on any set with n minus 2 elements should be the same as dn minus 2. So I claim that there are dn minus 2 such sigma prime. Okay, so what's the count in this case? We have n minus 1 choices for x, and any such choice can be paired up with any derangement that you get on the set n minus x minus n to give us a derangement on n letters that has the property that sigma x equals n. So in this first situation, we get a count of n minus 1 times dn minus 2 such derangements. Okay. Now, what happened in case 2? Well, in case 2, sigma x, okay, so our sigma is going to look a little bit different. We have a 1, 2, x, and x. So sigma 1, sigma 2, this is sigma x, which does not equal n. So in this case, the element n which should appear in the bottom row of the permutation sigma somewhere, is not under X. So it has to be somewhere else. So there is some Z which is not X, and under that Z, we are going to find our element N. Now, how can we count these permutations in this case? Same as before, there are n-1 choices for X, as again, X is not the element N, so it can be anything from 1 to n-1. And now we are going to do a similar construction as before here. So from sigma, we are going to construct a permutation sigma, let's call it double prime. And this is going to be a permutation on n-1 elements. So we have an X here, we have a Z, and it goes all the way to n-1. And in this permutation, we are going to leave everything unchanged from sigma. So this is sigma X, which was not N. This is sigma n-1. But you see here in the top permutation for sigma, Z gets mapped to N, and we are just going to change that in sigma prime to send Z to X. Okay. Now, at the bottom, it should be clear that we are, so in the permutation sigma, if we look at the second row, except for the last entry, what we saw was the set N without the element X. And now what we did is we took the N out and we replaced it by X in the permutation sigma double prime. So that tells us that sigma double prime is a legit permutation on n-1 elements. And actually, it is going to be a derangement. So I claim that sigma prime is a derangement. And why is that? Well, everything was inherited from sigma. So 1 is not sigma 1, 2 is not sigma 2, X is not sigma X, n-1 is sigma is not sigma n-1. And because we are in case 2, we have this additional hypothesis that the element that is mapped to N, this Z here, is not X. So here, because Z is not X, that tells us that sigma double prime is a derangement in Sn-1. And now the count is similar to the one before. We have n-1 choices for X, and there are dn-1 such sigma primes. So we can pair up any choice of X with any derangement from here, and we get a count of n-1 dn-1 such derangements. So if we add up this, the count from the first case with the count from the second case, that should be the total number of derangements in our in Sn. So I'll just write the proposition that we just proved is that the proposition that dn equals n-1 times dn-1 plus dn-2 for any n greater or equal to 3. Okay. Now we can use this to extend our computation of dn. So let's write them side by side, and dn and n factorial, which is the upper bound for dn. Again, let's go to 0 first. So here we have 0 and 1. If n is 1, we have 0 derangement, but we have 1 permutation. N is 2, we have 2 permutation and 1 derangement. N equals 3, we have 6 permutations, and we saw there are 2 cycles, so 2. What happens with 4? So we have 24 permutations. Well, this recurrence relation, if we apply it here, d4 equals 4 minus 1 times d3 plus d2, and is 3 times 2 plus 1 gives us 9. And so on. So you can do 5, you get 120 permutation. And if you compute D5 is 5 minus 1 times D4 plus D3, it's 4, and 9 plus 2 is 44. 6, 720, D6 is the last one I'll do, 6 minus 1, D5 plus D4, it's 5 times 44 plus 9, 5 times 53, so 265. So perhaps you're able to see a pattern, or perhaps you're not. It's useful, you get the value. I mean, it's always useful to get the values of a sequence for small values of the index. But what do we do now? How can we convert this information from the proposition, this recurrence relation, into some useful formula for our sequence? Before we do that, let me give you, so this recurrence relation was, I think, known to Euler, and Euler proved a nice, figure out a nice consequence of it, which is if you can write dn minus n dn minus 1. So if you apply it, if you use the recurrence above is dn minus 1, n minus 1, dn minus 1 plus dn minus 2 minus n dn minus 1. And this is going to be, if you unpack things a little bit, is going to be minus dn minus 1 minus n minus 1 dn minus 2. So here there's something going on, and we can create a new sequence. Let's call it, I don't know, fn, which is by definition, use different colors. Let's use fn is dn minus n dn minus 1, or let's say n greater or equal to 1. And what we get here is that fn, so the equation above says that fn equals minus fn minus 1, which will be the same as, if you apply it again, is going to be minus fn minus 2, and so on. So, which is fn minus 2, and so on. So this sequence fn just repeats with a period of 2. And I leave it to you as an exercise to figure out that dn minus n dn minus 1 actually will equal minus 1 to the power n. If you look at the initial values of the sequence fn, you will get that. So this is another nice recurrence relation. It's a consequence of the one that we found that was discovered by Euler. So let us try to find formula for dn now. So we'll give 2 proofs for the formula for dn. The first one will look much more complicated than the second one. So the first one involves the exponential generating function of our sequence dn. Is defined as g of t sum from n equals 0 to infinity of dn divided by n factorial t to the n. So it's very similar to the ordinary generating functions. It's just you have this extra n factorial attached to the tn. Okay. There's a whole theory about which sequences are more amenable to be solved using ordinary generating functions versus the ones that are can be solved using exponential generating functions. There's a very beautiful book by Herbert Wilf, and it's free. It's a free book online. Functionology, I think. And you can read more about it there, and also you can read more in the article on formal power series that I put on the Google Drive by Ivan Niven. All right, so now we are in this situation. We have this exponential generating function, and can we do something with it to figure out our original sequence? All right, so let's write. So we have GT over there. Let's do an operation that we haven't done before. Let's take a derivative. So what is the derivative of g of t? Well, it's the sum of the derivatives of each term. So it's going to be a summation from n equal 0 to infinity of dn n factorial. Well, let's just do maybe we do the derivative directly. So we're going to have a dn n factorial tn minus 1. Now, to make our life easier, let's look a little bit more carefully about the range of summation that we have here. In our sequence, d0 is 0 and d1 is 0. d1 is 0. d2 is 1. So our summation, we can start the summation actually, summation from n equal 2 to infinity of dn. N with n will cancel. So it's going to be dn over n minus 1 factorial times t to the n minus 1. And now we had this recurrence relation that we proved earlier, that dn equals n minus 1 times dn minus 1 plus dn minus 2, where n greater or equal to 3. So I want to apply this recurrence relation and move this dn from the top, replace it there. But that starts at 3. So let's peel off the d2 term first. So we get d2t plus summation from n greater 3 more dn divided by n minus 1 factorial t to the n minus 1. And now we kept d2t as it is, and then we sum. And now here we are going to replace dn by n minus 1 times dn minus 1 plus dn minus 2 divided by n minus 1 factorial times t to the n minus 1. t to n plus, we get two sums here when this sum expands. The first one is summation from n3 to infinity. N minus 1 with n minus 1 gives me an n minus 2. I have a dn minus 1, tn minus 1, plus summation from n equals 3 to infinity, dn minus 2 here, n minus 2 factorial, t to the n minus 1. Okay, so can we identify some of these sequences? Well, the first one here, let me move it here first. Change the color. This is going to be a summation. I'm going to change well, there are two things that will happen here. One, there will be a t as a common factor. And then when you take t as a common factor, this exponent from n minus 2 is going to, inside the summation, is going to go down to from n minus 1 is going to go down to n minus 2. And then we are going to change the summation here, and we are going to replace n by n plus 1. So this sum is going to go, so we have a t, and now it's going to go from 2 to infinity, And on the top, we're going to get dn. Here it's going to be n minus 1 factorial. And here it's going to be tn minus 1. It matches the factorial from the bottom. And now the other part that is left is going to be a d to t plus summation from n equals 3 to infinity of, so over there, what we're going to do, so the d to t from here, I'm going to combine it with this sum. I will take t as a common factor, and I will have a d2 plus summation from n equals 3 to infinity dn minus 2, n minus 2 factorial, t to the power n minus 2. But when n equals 2, when n equals 2. So this is good. Now, on the left-hand side, we have t times the sum from n equals 2 to infinity of dn n minus 1, which is exactly this sum over here. So this sum here, this equals g prime t. And here, this is a t, and the sum that we have over here to give us t. That is going to be g of t. So we should get g of t over here. So all this work we get that the thing that we started with, which was the derivative of g prime of t, equals t times g prime of t plus t times g of t. And from here, we get something of the form, you get the differential equation, g prime over gt equals t over 1 minus t. And you can solve this, and we get that g of t equals e to the minus t divided by 1 minus t. Okay, but how is this going to help us with our formula for dn? Well, we look at each of these two expressions. So first of all, 1 over 1 minus t, it's a summation for k 0 to infinity of t to the k. And e to the minus t, it's going to be a summation from L equals 0, say, to infinity of minus 1 to the L factorial t to the L. And using these two formulas and the rules of multiplication, we are going to get that e to the minus t to the 1 minus t is going to be a summation from n equals 0 to infinity. And here should be a sum from L equals 0 to n of minus 1 L factorial. This should multiply here by the coefficient of n minus L from the other series, but all those coefficients are 1, so it makes our life easier, times t to the n. So this part is a 1. So we get this this expression. But on the other hand, g of t was the summation from n equals 0 to infinity of dn over n factorial times t to the n. And so from these two, we get that dn equals n factorial times summation from L equals 0 to infinity minus 1 to the L. Okay, so that's the formula for a closed formula for the number of derangements on n elements. Now that formula can be used to say something more, and I give the details in the book, but I'll leave it to you to prove that e to the minus 1 minus dn divided by n factorial is going to be less than 1 over n plus 1 factorial. And from here, we get something of the form that n factorial over e minus dn is going to be less than 1 over n plus 1. I think this is for n greater or equal to 2. And using this result, one can prove that dn is actually the largest integer, which is less than n factorial over e plus 1 over 2. So dn is about n factorial over e. Remember, e is about 2.718. So e minus 1 appears here because if you look at this alternating sum here as a series, it's a convergent series, and it converges to 1 over e. So let's do now a different approach, and this different approach to determining the number of derangements is using the principle of inclusion and exclusion. So what's the scenario here? So here, let's say we have a big set A, finite, and inside it, we have some bad sets, let's say A1, A2, A3. And generally, you're going to have A1, AN, some sets inside A. All of these sets are finite. So let A1, A2, AN be inside some set A, finite sets, be finite sets. And what we want to count, we want to count the number of elements that are here outside of these bad sets. So the number of elements, we want to count the number of elements that are in A minus the union of A1, A2, AN. Well, it turns out there is a nice formula for this, the cardinality of this set. To give the formula, I need to introduce a notation, so I'll do it here. If we have J, a set of indices, which can be seen as a subset of the set from 1 to n, I'm going to define A index J as the following. The intersection of all subsets which index is in the set J, AJ, if J is not empty, and it will be defined as the big set A if J is the empty set. So clearly A empty set is A, but A, let's say I put the subset here 1 and 3, this is just going to be A1 intersect with A3. And now the principle of inclusion-exclusion can be stated very concisely with this notation. And it says that the cardinality of this set here is going to be a sum over all J in N of -1 to the power cardinality of j times the cardinality of aj. Now, I said can be stated concisely. That's why we like this summation notation. It's a small, short formula, but you should realize that the number of terms inside this summation is 2 to the n, because those are all the possible intersection between the sets A1, A2, and. Okay, let's state this again in a different way. So again, our first formula is cardinality of A minus A1 union AN equals the sum over all j in n minus 1 to the cardinality of j A intersect j, A subscript j. This formula is actually equivalent to a formula in which, let's say, now you want just the cardinality of the bad sets. Well, you can get this formula from the one on the top, just taking all the subsets here except the empty set that corresponds to A, and having a change of sign, which can be done by changing the exponent of -1. It's essentially the same. I mean, assume all of you have seen this formula before. It's the generalization of so if you have two sets, you have A1 union A2 is A1 plus A2, which is these are the two things you get when cardinality of j is 1, as in terms of subscripts, minus A1 intersect A2, which is a subscript 1 and 2. And similarly, you have a formula for A1 intersect A2, union A2. A3, their sums, sum minus the cardinalities of intersections of 2, plus cardinality of intersections of 3. Okay, so let's do an example with the derangements. So when we count the number of derangements, dn, derangements in Sn. So our scenario is as we have to figure out the bad sets and the big set A. Now the big set A is not too hard to figure out. It's the set of all permutations. Now here we're looking for these sets that we want to avoid. So what do we want to avoid? Well, A1, we could put it are all the permutations sigma in Sn that map sigma of 1 to 1. So you don't want that to happen. And then A2 is going to be similar. All the sigma in Sn, sigma 2 equals 2, and so on. Sigma of n equals n. Okay, so these are the bad sets. And then it's clear that the number of derangements, dn, is going to be the cardinality of A minus the union of these sets, A1, A2, An. So all we have to do now, we just first write down the formula from the principle of inclusion-exclusion, which we haven't proved. We'll prove it in a second. Going to be something like this. And now let's figure out what each of these things are. What is AJ? So when this is going to be Sn, if J is the empty set, so that's not difficult. Now, when it's not going to be the empty set, so AJ when J is not the empty set, is the intersection of all j in j of aj. And this consists of all the permutation sigma, such that sigma fixes every element of the set j. So sigma j equals j for every j in j. So all these elements, we know exactly where they go. They don't go anywhere, they are fixed. But you are free to do everything that you want with the remaining n minus cardinality of j elements. So you can permute them in all possible n minus cardinality of j factorial ways. So that basically is the cardinality of aj is going to be n minus cardinality of j factorial. And that actually works also when j is the empty set. The cardinality of a empty set is the cardinality of Sn, and it's n factorial, which is n minus 0 factorial. So we can use this formula and we can plug it into here. What do we get? We're gonna get the following. So let me write it this way: Tn cardinality of a minus a union an summation overall j minus 1 cardinality of j cardinality of aj n minus cardinality of j factorial. Now, when we go through all the subsets, let's go through them according to their cardinality. So here's going to be a bad notation. Let's just use k from 0 to n of summation over all j subsets of n. Cardinality of j is k of minus 1 of j n minus, well, if this cardinality is k, here I put n minus k factor. So it's going to be summation from k0 n. And here also I'm going to have a k. So I will sum up minus 1k, minus 1 to the k times n minus k factorial as many times as I have a j of cardinality k, which is n choose k. So this is sum from k equals 0 to n factorial to n of n factorial divided by k factorial times n minus k factorial times minus 1 to the k times n minus k factorial. These cancel, and we get the formula. We take n factorial as a common factor, and we get the formula from before. Okay. So that's that. We'll do more examples likely next class, but let me give you the proof of the principle of inclusion-exclusion, which is usually abbreviated by this nice word pi. So cardinality of a minus a1 union an equals the sum over all j n of the cardinalities of these intersections. Okay. So again, it's useful to think about the scenario of the set A again, and all these bad sets A1, A2, A. Okay. And what are we going to do is we take an element X in A, and we want to show that the element X is counted exactly the same amount of time on the left side of my equation as it's counted on the right-hand side. More precisely, so we have two cases. If X does not belong to A1 union AN, so that's the first case, then clearly X belongs to A minus A1 union AN. So X is somewhere here. That's case 1. So in that case, the contribution of X on the left-hand side is clearly 1. because the left-hand side is exactly this set here. So that's clearly 1. What is the contribution of x on the right-hand side? On the right-hand side. Well, to see that, note that the contribution x contributes 0 to any aj, cardinality of aj, when j is not an empty set, because such a aj will be the intersection of some sets ai, but x is in none of them, so it doesn't get counted. But x contributes 1 to a empty set, because x is contained in a empty set, which is A. So therefore, its contribution to the right-hand side is also 1. What is case 2? Where x belongs to A1 union AN. So again, we have this A, we have our A1, A2, AN, and maybe our x is somewhere here. And in that case, so what were our left and right hand side? So the left hand side was A minus the union. This is the left hand side. So in this case, really the element x contributes 0 to the left hand side because it's not there. What about the right hand side? The right hand side is the summation over all j subsets of indices of this quantity. So now x belongs to the union. So it means that it belongs to some sets. So let's just write down precisely those sets to which x belongs to. So without loss of generality, let's just say that x belongs to A1 intersect AL, and x does not belong to AL plus 1. X doesn't belong to AN. Okay, so it belongs to some. It could belong to the 1st, 5th, and 7th, but let's just relabel the sets such that are the first L. So in that case, what is going to be the contribution of x? Then x contributes 1 to, so contributes 1 means is counted to a set AJ whenever, if and only if, the set J is a subset of these indices 1 to L. Because AJ is the intersection of J in J of AJs. So X appears in such intersection if and only if the set of indices is a subset of 1 to L. And X contributes 0 otherwise. So with that in mind, we can, the contribution of x to the sum to the right hand side is going to be what? Well, it's going to be a summation. So we go now over all the subsets. So over all the subsets of these indices. So it's going to be summation over all j, but j is a subset of the set L, and it's going to be -1 cardinality of j. And there's going to be a 1, which is the contribution of x. Now we split these j's according to their cardinalities. So let's just use as a cardinality for j k as before. So it's going to be summation from k equals 0 to L of the sum over all j's subsets of L of cardinality of j equals k -1 to the k. And this is going to be summation from k equals 0 to L. How many subsets are like that? There are L choose k of them times -1 to the k. So I'll just write these small letters from there. I'm going to expand them here. This is going to be summation from k equals 0 to L of L choose K times minus 1 to the K. And by the binomial formula, this is the same as 1 minus 1 to the L, which is 0. And here we use the fact that L is greater or equal to 1. That's what makes this. And that's the proof of the principle of inclusion-exclusion. Next time, we will do some other applications of the principle of inclusion-exclusion. And later on, we'll talk about the Mobius inversion formula, which is a very powerful generalization of the principle of inclusion-exclusion.